Hi to all of you. Today we are going to start a new chapter, that is the theory of simple bending. So this is the lesson for the day 41, and our new chapter is theory of simple bending. Now, so I'm sharing the PPT prepared for the today's lesson. Here we are going to discuss about some basic definitions, concepts of simple bending, and also assumptions that are made in the simple bending. Now coming to the previous classes, we have studied force system, we have studied the stresses and the strains, geometrical properties of sections, and also shear force and bending moment diagrams. So the knowledge of the above chapters are required here. So in the previous classes we have studied about the beam, bending moment, shear force, force like that. Now actually what is a beam? A beam is nothing but a member which is subjected to the external forces which acts at right angles to the axis of the beam, or nothing but the which acts at right angles to the longitudinal axis. So here beam means it must be loaded with some external loads, so that the load will always act at right angles to the axis of the beam. And then what is the bending moment? The bending moment is nothing but the algebraic sum of the moments of all the forces about any point in the plane of the beam, either to the left of the section or to the right of the section. So this bending moment is already clearly defined in the previous classes. The shear force, what is the shear force? So the algebraic sum of the force that is acting either to the left of the section or to the right of the section is called the shear force. Now in this class we are going to discuss about the some basic terms related to the theory of simple bending. So first of all we'll define what is the simple bending, then what is the section modulus, and what is the moment of resistance, and also we'll discuss about the assumptions made in the theory of simple bending, and also if time permits we'll discuss about the bending equation. Now whenever a beam is subjected to some external loads, it also subjected to shear forces and bending moments, and the beam is made up of a material having some section. It may be rectangular section, or it may be square section, or it may be circular section. So whenever a beam is subjected to some amount of external force, so it is subjected to some certain deformation. So it undergoes some deformation, and due to this, what is happening? Due to the the external forces acting on the beam, it undergoes deformation and some stresses will develop. So, so whenever a load acts on the beam, what happens? The beam will try to resist that external force. That means it will develop the internal resistance. So at any point, the amount of internal resistance offered by the beam is also equal to the external force acting at that point. So these internal resistances are nothing but the stresses developed in the material, and so the stresses developed due to the bending moment. So whenever a beam is carrying some external load, it is subjected to some amount of bending moment, and due to this bending moment, it is subjected to some kind of bending stresses. So the stresses developed in the beam due to the bending moment is called as the bending stresses. So now here we have to define a term, bending stress. What is bending stress? Whenever a beam is subjected to certain external loads, what happens? Some shear forces will develop and some bending moments also will develop, and so that will lead to the development of the bending stresses. So the stresses developed due to the bending moments in the beam is called as the bending stresses. And here, before going to define about the simple bending, we have to define the neutral axis, neutral layer, and section modulus. So here, what is this neutral layer or the neutral axis? If we take any cross section of the beam, if we take the cross section of any beam, for example, we take the rectangular cross section. So now we are assuming that the cross section of the beam is made up of so many layers of very small thickness. So it is made up of, so many layers. So it is consisting of so many layers of small thickness. So here each individual layer is free to expand or contract without depending on the other layer. So here what is happening is whenever the beam is subjected to some external load, and here we got the top layers, that is the top side of the outermost surface of the beam is called the top layers, and innermost surface of the beam is called the bottom layers. Here what is happening is the top layers may subjected to some tension, and the bottom layers are subjected to some kind of compression. So here that means the top layers are the top layers of the beam are being shortened, and whereas the bottom layers of the beam are being stretched. That means the top layers of the beam are subjected to the compressive force, and whereas the bottom layers of the beam are subjected to the tensile force. So in this way, the tensile stresses and the compressive stresses are developed in the beam. So these are called as the bending stresses. Now coming to the basics and definition of the theory of simple bending. So actually Now we have defined what is the bending. What is the bending? Tell me what is the bending? Whenever a beam is subjected to external loads, so some kinds of bending stresses are developed. Some kinds of stresses are developed due to the bending moment acting on the beam. So that stresses are called as the bending stresses. And as a result of the beam will deflect some amount from the normal horizontal axis. So the amount of deflection is called as the bending. Now simple bending. What is the simple bending? If the so generally whenever a beam or any material is subjected to certain amount of external load, what happens here? There are the two kinds of loads are acting. So one is the shear force and other is the load due to the external force. So generally, but here what is happening is the amount of shear force acting is some sometimes very less, and also if we take into account of that shear stress acting on the member, the study will become a complicated. So generally, for the easy analysis of the member, the sometimes we neglect the effect of the shear forces in bending. So if we study the bending of the members without considering the effect of the shear force, then it is called as the simple bending. And the other name for the simple bending is pure bending. So generally pure bending and simple bending both are same. That means here only the bending of the beam due to the external loads are considered. So here there is no question of consideration of the shear force and its contribution for the bending. So here the bending of the beam that is not accompanied by the shear force is called the pure bending or simple bending. So in the simple bending, the effect of the shear force is neglected or the effect of the shear force is eliminated. Then that bending is called as the simple bending. Now coming to the neutral layer. So what is this neutral layer? So if we take the cross section of any beam, so it is just like a rectangle cross section like this. So it is having a rectangle cross section. Now like this. So here this is having some thickness. So here this is called the top layers and this part is called the bottom layers. So here what is happening is this cross section of the beam is assumed to be consisting of number of thin layers and each layer is independent of the other. That means each layer can able to expand or contract without depending on the other. Then in this case, so the beam is made up of number of layers and here so this is called a top layer and this is the bottom layer. So whenever a beam is subjected to certain amount of external loading, here what is happening is for example like this. So we applied like this. So this is the initial cross sectional beam and due to the action of the force, so it became like this. That means it will turn like this. That means what happens? Here the top layers are shortened. That means the length of the the length of the top layers are decreased, whereas the length of the bottommost layers are increased. Here, what, for example, like this. So whenever you say we take that means the straight beam is now becoming bent like this. That means the straight beam, this is a straight beam. The straight beam is bending like this. That means it is forming a curvature. If you assume that the center of this curvature is somewhere here, the radius of this innermost layer is lesser, whereas the radius of this outermost layer is more as compared to the innermost layer. So that means here the radius is less and here the radius is more. So this part is subjected to the compression and this part is subjected to the tension. So the innermost layers are subjected to the compression, whereas the outermost layers are subjected to the tension. So innermost layers are subject to compression and outermost layers are subject to the tension. And here, so if this is the innermost layer and this is the outermost layer, so there is a midpoint of this top layer and bottom layer. So that midpoint of the top layer and bottom layer is nothing but the position of the neutral layer. That means that layer. So here what is happening is the top layer is subjected to the compression and the length shortens, whereas the bottom layer is subjected to the tension and the length increases, whereas the intermediate part of the intermediate part of the section, that is the intermediate layer, that is which is equidistant to the innermost layer and outermost layer. So that length will not change and that layer is either not subjected to the compression or tension because its length will remain constant. Then it is not subject to any kind of compression or tension force, and that layer is called as the neutral layer. So neutral layer means the layer which is not subjected to the either tensile force or the compressive force due to the bending of the beam, and it is not subject to any kind of force is called as a neutral layer. So the length of the neutral layer is unchanged. So it does not subjected to either compression or tension. So therefore the length will remains constant or the length will remains unchanged even it is bent into some radius. Then that layer is called as a neutral layer, and the radius at which the neutral layer bends. So for example, if the beam bends like this is a straight beam and due to the load it bends like this. When it bends like this, the neutral layer is the layer and at which the length of the beam does not change is called a neutral layer, and the radius at which the neutral layer bends is called as the radius of curvature. So generally it lies at the midpoint of the outermost layer and innermost layer of the section. So that means the neutral layer means it is very important. Whenever if we take any cross section, we got the top layer and bottom layer. So the midpoint of the top layer and bottom layer is the neutral layer. For example, if it is a rectangular cross section, we can say it is a midpoint. If it is a I section, then we have to take the centroid. The that is nothing but the centroidal axis. So that axis does not subjected to any change in length, and that length will remain unchanged, and hence it is not subjected to any kind of force, either tension or compression, and that layer is called as the neutral layer, and the radius at which the neutral layer bends is called as the radius of curvature. Now the moment of resistance. So here what is happening? So whenever a beam is subjected to some number of external loads, what happens whenever a force acts? So it creates some moment about any point along the length of the beam. So the moments, so whenever that means, so always the whenever a beam is supported at some supports and it is subject to loading, even the beam is not moving. That means the beam is in the equilibrium condition. In that condition, the whatever the forces acting, the external loads acting on the beam will create some moments. So the algebraic sum of the all moments of all the forces is called as the moment of resistance. So the word, the algebraic sum of the moments of all the forces about any point in the plane of the beam is called as the moment of resistance. And generally, if we come to the definition of the bending moment, the bending moment also, the by definition, the bending moment also the algebraic sum of the moments of all the forces about any point, either to the left of the section or to the right of the section, is called as the bending moment. Similarly here, the algebraic sum of the moments of all the loads which are acting on the beam about any point in the plane of the beam, either to the left of the section or to the right of the section, is called as the moment of resistance. And generally the moment of resistance of a beam is equal to the bending moment of that beam at any point in the plane of the beam. So the moment of resistance is nothing but the bending moment acting at any point on the beam. So the moment of resistance also equal to the bending moment. So here moment of resistance means this is the internal moment, internal resistance of the beam, and whereas the bending moment is the external moment. So for the equilibrium of the beam, the moment of resistance is also equal to the bending moment. So MR is also equal to the BM. Next, the section modulus. So the section modulus means it is denoted with the letter Z, and it's all the value of this Z will depend on the shape of the section. That is the shape of its cross section, and generally it is a ratio between the moment of inertia and the distance between the outermost layer and the neutral axis is called as the section modulus. So the ratio of moment of inertia to the distance between the outermost layer and the neutral axis is called as the section modulus of the beam, and it is always denoted by the letter Z, and Z is equal to I by Y, where I is called as the moment of inertia of that section and y is the distance of the outermost layer from the neutral axis. So as I said, so this is the beam. For example, this is a beam, and this is section, cross section of the beam, and here it is called the top layers. This is the bottom layers. So whenever it bends like this, what happens whenever? So this is the beam, and when it bends like this, so this is the outermost layer. So this is the innermost layer, and in between we got a neutral axis. So the distance between the neutral axis and the outermost layer is the what? That is the y, and generally the y is equal to half of the thickness. Generally, suppose we got a depth of d, then for the rectangular section y is equal to d by 2. So generally the half of the thickness will be the distance of the outermost layer from the neutral axis. Generally the neutral axis will act from the midpoint. So if it is having a uniform thickness, then half of the thickness will be the y. So the section modulus is equal to z is equal to I by y, where I is called the moment of inertia and y is called the distance of the outermost layer from the neutral axis. Next, coming to the bending equation. So here in case of the theory of simple bending, so we must know the bending equation. So we got some equation. So this equation will carrying a 6 terms. There is m I sigma y e r. So these 6 terms are very important, and we got the relation between all these 6 terms, and this gives the bending equation. And generally, in case of this theory of simple bending, we may have to find out the stress, or we may have to find out the bending moment, or we may have to find out the moment of inertia, or we may have to find out the radius of curvature. So any unknown quantity can be found by using this equation, and this is called as the bending equation. So here m by I is equal to sigma by y is equal to e by r is called as the bending equation, and here m is the moment of resistance. So that is nothing but the bending moment at any point on the beam, and I is the moment of inertia of the section of the beam, and here sigma is the bending stress acting on the beam, and y is the distance of the neutral axis from the outermost layer, or the distance of the outermost layer from the neutral axis, and E is the modulus of velocity of the material of the beam, and R is the radius of the curvature of the beam. So when that means when it is at bending subject to external loading, it bends. That means it forms some curvature. So the radius of curvature of the neutral axis is called as the R. That is the radius of curvature. Next here we got some assumptions. So in the theory of simple bending or pure bending, we have made some assumptions to derive this bending equation. So that assumptions are very important from the subject point of view, and we must know what are the assumptions made, then only we can able to clearly understand the theory of simple bending. So first thing is the beam is initially straight and unstressed. That means so this is the beam. So this beam is initially straight. That means it is initially it is not having any curvature. It is not having any bending. So initially the layers of the beam are straight, and also it is not subjected to any forces. That means it is not stressed. The layers of the beam are not stressed. So then that is the first condition. That means the beam is initially straight and unstressed. This is the first condition. The next one is the material of the beam is homogeneous and isotropic. So what is the meaning of this homogeneous? That means if the material is having the same density at all the points, then it is called as the homogeneous. That means the density is uniform throughout the beam. Then we can say that the beam is having the homogeneous density. That is, the beam is homogeneous throughout. Next, what is isotropic? That means if the beam is having equal the equal values for the elastic constant, both in compression and also tension. Because here what is happening is whenever the beam is subject to some external loading, it will bend, and during the bending the innermost layers or the top layers are subjected to compression, and the outermost layers or the bottom layers are subjected to tension. So innermost layers are subject to the compressive force, and the outermost layers are subject to the tensile force. So here the modulus of elasticity of the material should remain same either in compression or in tension. So that is called as isotropic. That means it should have the equal elastic properties in all directions, whether it is in compression or whether it is in tension. So the second point is the material of the beam must be homogeneous and isotropic. So this is the second point. Now coming to the third assumption. The beam has constant cross-section area with an axis of symmetry. So generally the axis of the symmetry is vertical. That means the beam must have a symmetrical axis. The cross section of the beam must have a symmetrical axis. That means it should be having the the shape of the cross section must be symmetrical about the y-axis. That means y-axis should divide the cross section of the beam into exactly two equal halves. That is, the cross section of the beam must be symmetrical about the y-axis. Now the following, this is the third point. Now the following are the some of the cross sections which are having the symmetrical axis about the y-axis. So first of all, you take this is a rectangular section. So here also it is symmetrical about the y-axis. So this is a T section. It is also symmetrical about the y-axis. So this is a C section. This is the I section. So this is called the built-up I section. So it is a circular section. It is a triangular section. So whatever the shape of the cross section, so it must be symmetrical about the y-axis. So the third point is the beam has constant cross-sectional area with a axis of symmetry about the y-axis. Next, the fourth point is the Hooke's law is obeyed at all points. That means the stress is proportional to the strain at all points in the beam, and the stress to which the material is subject to does not exceed the elastic limit. So at any point in the beam, the stress induced should not exceed the elastic limit. The fourth point is the it should follow the Hooke's law. That is, at all points the stress developed is proportional to the strain, and also the amount of stress developed at any point on the beam should not exceed within its elastic limit. Should not exceed its elastic limit. So this is the fourth point. That is the it should follow the Hooke's law, and the maximum stress developed should be within the elastic limit at any point in the beam. Next, the fifth point is the plane transverse sections remain plane and normal after bending. That is, there is no distortion of the cross section. For example, so this is the beam, and this beam is having a rectangular cross section. That is, so it is a length, this is the width or depth. So the plane means, so it is having a straight plane. So this is the having a straight, oh, it is a section, this section is having a transverse section means it is straight. That means before bending it is having a straight section, that is a straight line. Now after bending also the section will remain transverse. So it shouldn't bend. Even so, before bending and after bending, the section must be transverse. That means before applying the load, generally it is having a straight section. Even after applying the load, even it bends. What is happening is it forms a curvature, but that curvature is having a long radius, very large radius. And if we take a small part on that curvature, so it is appears to be a straight line. That means, so the section must be transverse even after the bending. So the plane sections which are transverse will remain plane and normal after bending. So there is no distortion of the cross section. So the cross section should not change. So initially whatever the cross section of the beam is having, the same should be there even after bending. So it should not change. So that is the meaning. Next, the other point. Every layer of the material is free to expand or contract longitudinally and laterally under the stress and do not exert pressure upon each other. So, so this point we already discussed. So here we are assuming that the cross section of the beam is made up of so many layers having the small thickness, and each individual layer is free to expand or contract. That means, so that layers are not bonded with each other, and the expansion or the contraction of the layer should not be affected by the other layer. So it is free to expand in the lengthwise or in the widthwise, and it should not exert the pressure or the force or resistance on the other. So this is the other part. Next, the value of the Young's modulus E for the material must be same in tension and also compression. So this is the isotopic property. The Young's modulus must be having the same value in case of the tension or the compression. And next, we will take the derivation of this bending equation, and to have the derivation, so first of all we should draw the cross section of the beam, and we have to consider the cross section of the beam, then accordingly we have to proceed. So for example here, so this is the what ABCD is a small element of the cross section of the beam, and this is the thickness we have shown here, and this is the neutral axis. The dotted line will represent the neutral axis. So generally it will be acting at the half of the thickness. For example, this is total thickness, then this is at the midpoint, it will act. This is the neutral axis. Generally it will act at the centroid of the section. This axis will pass through the centroid of the section. That's why it is called a neutral axis. And here now we are considering a small strip XX, which is at a distance of y from the neutral axis. So that is the distance between the neutral axis and the strip is y, and the length of the what is this, the length of the strip is equal to dx. Okay, so consider a layer xx in the beam at a distance of y from the neutral axis, and then and after bending this, so this is the before bending. Now after, this is the initial condition of the beam, and after applying the load, that is due to the external load, due to the action of the external load on the beam, what happens, the beam is subject to bending. So this is the condition of the beam after applying the external load. Now what happens, so this is AC, this is the inner layer. So here A1 C1, so the AC will become the A1 C1. So this is the innermost layer. And what is this BC BD? BD is the outermost layer before bending. Now here the BD will become the B1 D1 after bending. Now, so here this is the neutral axis NN. So here also N1 N1 is the neutral axis, but however the length will remain constant. Here also, so one thing we have to remember, the length of the neutral axis will not change. The length of the neutral layer will not change. It will remain unchanged before the bending and after bending. So that is very important. And here, so this is the figure. So when the load is applied, what happens? It starts bending. So this is the curvature. And generally, so we should take the radius of curvature at the midpoint. So that is at the neutral axis. So this neutral axis also will bend in the form of a circle or arc of a circle, and this arc will have some radius and will have the center point at somewhere else, and this is the radius at which the neutral axis of the beam is bending. So R is the radius at which the neutral axis of the beam is bending. So this is the R and this is the Y. The Y is the distance between the neutral axis and this small elementary strip that we have constructed here. So this AC will become the A1 C1, and BD will become the B1 D1, and this N will become the N1 N1, and this is the radius. Now Coming to the initial part, let AB and CD represent the two transverse parallel sections of the beam, and A1B1 and C1D1 be their positions after bending as shown in the figure. Now after bending, the planes A1B1 and C1D1 subtend in angle theta at the point O, and R be the radius of the curvature. So up to here we have studied, and here this is the length of the strip before bending is equal to xx, and this is the initial length. So initial length is equal to what happens from this figure. Initial length xx is equal to, here this is the xx is also equal to nn. So nn is also equal to n1 n1. So that is nothing but the r into theta. So this is the angle, theta is the angle subtended by the radius of curvature at the center point. So xx is equal to r theta. And now today, coming to the summary part, we have discussed about the basic concepts of the simple bending, that is the theory of simple bending, and we have defined the moment of resistance, and what else section, that is we have defined the moment of simple bending, neutral air, moment of resistance, and section modulus, and we have defined the bending equation. Now at this point today we'll stop the lesson, and next class we'll continue the same lesson from this point. So I'm stopping the sharing of this PPT, and I'm ending the meeting. I'm ending the class. So thank you all of you